Hello everybody and welcome back to my channel. This is Dave. In this video, we're going to be looking at yet another Sangaku geometry question from Japan. This question originates around 1806, and what's interesting about it is that it uses some of the fundamentals of calculus. Although it must be said that the Japanese did not independently evolve a theory of calculus, this shows that they were making some steps in that direction before they opened up to the rest of the world. In this question, our task is to maximize the area of the rectangle that is inscribed in the triangle ACE. In this video, we'll be looking at it two ways. First of all, we'll be looking at it using calculus. And second, we'll be looking at it using an older method which does not involve calculus. In this question, triangle ACE is a right triangle. We assume that point D can be moved along the hypotenuse CE, and our goal is to find BD and BA in terms of AE and AC respectively that maximizes the area of the rectangle ABDF. To proceed, we will first label BD and assign it a length of x. Next, we will assign DF a length of y. After this, we will assign the short leg of the large triangle, AC, and we will give that a length of q. And finally, we will let AE have a length of p. We can note right away that triangle BCD is similar to ACE since they are all right triangles. This will allow us to write the ratio BD over AE is equal to CB over CA. We can then substitute the variables x, y, p, and q in order to make our job a little bit easier. So this gives us x over p is equal to q minus y over q. Rearranging this slightly, we get x over p is equal to 1 minus y over q, and rearranging that so that we can get y on the left-hand side, we will get y is equal to q times the quantity 1 minus x over p. What we have now is area as a function of x, and we can rewrite this as xq minus x squared q over p is equal to a of x. According to calculus, to maximize any function, we take the derivative with respect to x and set it equal to 0. This gives us q minus 2x times the quantity p over q is equal to 0, and solving this gives us x equals p over 2. If we recall that y is equal to q times the quantity 1 minus x over p, we can substitute the value that we just got for x and find that y is equal to q over 2. In other words, the area of BDFA is maximized when D is the midpoint of CF. That is to say that BD will be exactly 1/2 of AE and DF will be exactly 1/2 of CA. As we said in the very beginning of this video, using this calculus method is a relatively newer approach. A more traditional approach would be to recognize that the function for area is in fact a quadratic function. That is to say that xq times the quantity 1 minus x over p will give us a quadratic when we multiply it out. This being the case, the vertex is always located exactly in between the two roots, and we can set the equation itself equal to 0 and then solve for x. So this gives us xq times the quantity 1 minus x over p is equal to 0. Since the product is equal to 0, each factor must be equal to 0, and this gives us x equals 0 or x equals p. The vertex must be located exactly in between these 2 points, so therefore in order to get the maximum, we only need to take the average of 0 and p. which naturally is p over 2. Now, if we insert x equals p over 2 back into the equation for y, we will get q over 2 as the length for y. Again, this is exactly the same answer as we got by calculus. So this is the solution to this question. If you enjoyed my video, please give me a thumbs up and subscribe to the channel. Thank you very much, and I'll see you in the next video.